question 1 says show that it's unbiased, right? So we're going to go through the same steps that we go through every time we're asked. What we're trying to show is that the expected value of this estimator of the population parameter is equal to the population parameter. Okay, so we show this is equal to beta 1. And so again, we start by substituting in for yi. Beta 0 plus beta 1. Okay, so that's our true model. I'm just going to leave the bottom the way it is. And the same things kind of happen. We have this beta 0 that we can split out. So what we're left with at the end of the day, right, because that equals 0 and that equals 1. My goodness, my pens are not performing up to par today. So remember, we still haven't taken the expected value, but what we're going to look to do is take the expected value of what we're left with, which is beta 1 plus Ci minus okay, so we're going to look to take the expected value of that. So this is for part A. So we run this through, and it's just like, remember z is a linear function of x, so we're going to treat it just the same as we would with x. Plus all of that. And so remember, this equals 0, which reduces this whole thing to 0. And so we're left with just the expected value equals beta 1. Now when we take the variance, again, we're going to be left with this top part. Squared and the bottom squared. And so remember, for each observation, this is going to equal the same thing, right? Because they're all independently drawn from the same distribution. And so we can pull this sigma squared out, and what we're left with is the following. Or an easier way to write this is just SXX over SZX. And actually, it might seem like I just kind of made this up, but actually we're going to talk about when you would use this. There's actually going to be a practical reason why we use this. There'll be certain instances when this is actually an unbiased estimator, when our OLS estimator is biased. That's something we'll talk about after the test. But for now, just assume it's kind of made up. But we will come back to this form, right? This is going to be the IV estimator, the instrumental variables estimator. Okay, so the next part is what we're going to do is, okay, we've seen that this is an unbiased estimator. We also know that if we compare this variance of beta 1 hat to, right, so that is going to be right, with just the spread of x on the bottom. So the question is, right, we have two variances, which one's bigger, right? We know that they're both unbiased. So the question is, which one's bigger? And sort of the spoiler is that this one's always going to be minimum, right? It's blue. So it's going to have the lowest amount of variance no matter what. But let's see, I guess I'll get the screen back up. So this is just the way that I calculate it. I found it was easiest to do it in SAS, or not in SAS, in Excel to do, just to illustrate what it is.
On the test, if we have a question like this, do we have to calculate it, or since we know it's the minimum, can we just say?
I mean, you'll have a calculator, but I'm probably, you'll be able to do anything with a calculator in a reasonable time, hopefully.
But do we have to, since you just told us that it's always gonna be the minimum one?
Well, it depends on the question. See, so for part C, you wouldn't have to calculate anything, but for part D, when you're asked to calculate that ratio, then you actually do have to calculate what those values are. So if I give you values, you have to calculate them. If I don't, yeah, then you should know, if those assumptions are met, this is always going to be the minimum variance. Oh yeah. I was thinking this is. Let's try that again. It has an autofocus on it. Seems like it. Okay, it's a little better. All right, so if I take these values of x, right? So x is just 1 through 10, and then z is so I have an equation here: 1 plus a plus b times the natural log of whatever a is. So here I basically have z and x. So from those two things, right? If I'm comparing the relative ratio between these two, it doesn't matter what sigma squared is because that's the same for both of them. So really what I'm going to do is I'm going to take this variance and divide it by that variance. And so in order to calculate the variance of beta 1 hat, which, so this is going to come from our OLS regression, right? I calculate these things. So here, right, I have xi minus xi bar squared, zi minus z bar times xi. Then I flip it just, I don't know, to illustrate that they do equal the same thing, right? And then zi minus zi bar squared also. So I calculate all those things, and you can see that, it's pretty easy to get for variance of beta 1 hat because you're just looking at the spread in x. So you do that pretty easily. For beta 1 tilde, you have to take, on top, you have zi z bar squared, and then on the bottom you have, and actually that is squared. So for that I calculate s x z and then square it. And so divide one by the other. And so the relative ratio I get is about 0.9. So this estimator is about 90% of this estimator. Okay. So, which is kind of what we expect. So the relative efficiency is 90, I guess 90%. Okay, so that's all there is for homework 3. Like I said, I'll have those. I'll put them in my box. You guys can get them at any point tomorrow. Let's start